Welcome to the deep dive. Today we're tackling, well, it's kind of the giant hungry elephant in the room of modern tech. AI's energy footprint.
Huge.
Yeah, we're building these amazing systems. They write, they drive, discover drugs, but wow, they use a staggering amount of power.
And it's accelerating fast. The global demand, it's getting to a point where it might just collapse under its own weight if we don't find a solution.
That's the fear.
Exactly. Because when we talk about these big AI models in data centers, you're usually looking at conventional computing, von Neumann architecture.
Right, the processor's here, memory's over there.
And they're constantly talking, electrons zipping back and forth through, a pretty big pipeline.
And that movement, that's the problem.
Physical shuttling of data, yeah. That's where most of the energy gets lost. Heat inefficiency.
It's the classic bottleneck, just fundamentally inefficient. So, okay, let's unpack this.
Let's do it.
Our deep dive today is all about the material science way out of this energy mess. People sometimes call it green AI.
That's a good term for it.
We're looking at the work of Miranda Schwacke, an MIT PhD student. Her research is in neuromorphic materials.
Ah, yes. Taking inspiration from the brain.
Exactly, trying to bypass that whole bottleneck by copying the most efficient computer we know.
And her work fits squarely into neuromorphic computing. It's not about tweaking software,
Right.
It's about rebuilding the hardware itself.
Designing chips that mimic how neurons connect.
Precisely. Building hardware that structurally, functionally acts like a neural network. Moving the computation away from a separate CPU.
And into the memory structure.
You got it. Integrating it.
Okay, and this is the fun part. The starting point for her thinking, the sort of foundation, involved baking a sturdy gingerbread house.
That analogy, it's actually quite brilliant.
So our mission today is to trace that journey. How does a kitchen experiment lead to a computer chip that learns like a human brain?
It really shows how fundamental principles just cross disciplines, The structure of any material, whether it's flour and sugar or tungsten and magnesium.
Determines how it behaves, its function.
Exactly.
Okay, let's start in the kitchen then. Before she was innovating with ions, Schwacke was part of MIT's Kitchen Matters group.
Right. They use cooking to teach science concepts, chemistry, physics.
Makes science very tangible.
It does.
Yeah.
And the experiment she described was about mechanical strength, material consistency.
So, gingerbread houses.
Yeah, she was playing with a recipe, specifically cutting back the butter in the dough
Less butter.
and observing how that change affected the final cookie. The texture, how sturdy it was. Could it hold up as part of a house?
So we're not just talking taste here. It's about, like, the crystal structure. Butter's a fat, right?
Right. And reducing the fat changes how the starch, the sugar molecules, how they all crystallize and link up when you bake it.
You're literally engineering the cookie's internal structure, making it strong or brittle.
That's it. Exactly. And realizing that tweaking minor ingredients fundamentally changes the macro scale structure and therefore the performance.
That's the same idea used in designing these advanced green AI chips.
Precisely. It's like defect engineering, but you can see it and taste it.
That really clarifies the connection. And her background seems almost tailor-made for this kind of thinking. She grew up in Charleston, South Carolina, and had these sort of dual science influences at home.
Yeah, her mother was a marine biologist with NOAA, studied dolphins, pollution.
So science for protecting the planet.
Right, that sustainability drive. And then her father was an electrical engineer.
The builder side.
Exactly. Got her into first Lego League, building robots to solve problems.
So you have that eco-consciousness and the hands-on engineering combined.
Right.
And she found materials science in high school.
Yeah, she saw it as this perfect intersection. Physics, chemistry, engineering, all rolled into one.
The ideal toolkit.
And her early research on dye-sensitized solar cells, that seems to be the spark.
Connecting materials directly to energy innovation.
Right. She realized that the big impact, the sustainable solutions, often come down to the nitty-gritty properties of the materials themselves, at the atomic level.
Which loops us right back to the core problem neuromorphic computing is trying to solve, that von Neumann bottleneck we mentioned.
The memory separate from processing.
All that data movement. It's wasteful, generates heat, drains power. We really need something better.
And the something better model is sitting right between your ears, the human brain.
Incredibly efficient.
Amazingly so. Because it doesn't shuttle data around like that. The key parts, the synapses, the connections between neurons, they do both jobs.
Storage and processing in the same place.
At the same time, they're like these tiny integrated circuits constantly being tuned, strengthened, or weakened based on activity.
That's learning, essentially.
That is learning, physically embodied.
So Schwacke's work at MIT under Professor Bill Gieldes, it's about creating hardware that copies that synaptic function.
Yes, but using electrochemistry. That's the specific angle.
Electrochemistry, not just electrons.
Right. She's designing what are called electrochemical ionic synapses, tiny devices you can tune.
How?
By adjusting their conductivity, making them better or worse at passing a signal, mimicking how real neural connections get stronger or weaker. That's how the system learns. And it's a really crucial difference from standard chips. Traditional silicon relies on electrons flowing super fast, pure charge movement.
Okay.
These devices, they rely on the physical movement of ions, atoms with a charge. It's slower, maybe, but more stable.
And that movement actually changes the material?
Yes.
Yeah.
It physically alters the material structure to store the information.
Yeah.
And that gives you the non-volatile memory you need. The info doesn't disappear when you switch it off.
Okay, so let's get specific. The ingredients, if you will. The source material says she's focusing on magnesium-based devices, magnesium ions. We hear about lithium ions all the time in batteries, sometimes hydrogen. Why magnesium? What's special about it?
Well, it mostly comes down to charge and potentially stability. Lithium, hydrogen, they carry a single positive charge, right?
Yeah.
$1 plus. Magnesium carries a $2 plus charge. It's divalent.
So double the charge per ion.
Exactly. Which means, theoretically, when you move one magnesium ion into the material, you could change the electric properties twice as much. Or perhaps more effectively.
More bang for your ionic buck.
Sort of, yeah.
Yeah.
It could allow for, stronger or maybe faster changes in that synaptic connection strength.
There's always a but.
There's always a but in material science. Magnesium is also a much larger ion than hydrogen or lithium.
Harder to move around.
Much harder to force into the crystal lattice of another solid material and get it to diffuse reliably. Especially being doubly charged, it interacts strongly. It's a real challenge.
So what's the host material? What's it diffusing into? The source mentioned tungsten oxide.
Right. Tungsten oxide is the host matrix. You could call it the solid-state electrolyte in this context.
And when the magnesium ion gets pushed in there with voltage...
It doesn't just sit passively. It actually changes the tungsten oxide's internal structure. Often it interacts with oxygen atoms, creating or removing vacancies, empty spots where an oxygen atom should be.
These are defect sites.
Exactly. So you're engineering these defects in real time using the ions.
And changing the defects changes the conductivity.
Precisely. By moving the magnesium ions and fiddling with these oxygen vacancies, you're fundamentally altering the electronic band structure of the tungsten oxide.
Which changes its electrical resistance.
Dramatically. Low resistance could mean the synapse is strong, the connection is learned. High resistance, it's weak. That resistance changes the memory. It is the learning.
It's fascinating because, as Professor Yildiz pointed out, this is really a new frontier for electrochemistry.
It absolutely is.
Taking something usually associated with batteries or fuel cells
Energy storage.
and applying it to computing, information processing.
The potential is huge. Not just the energy savings from using slow, stable ions instead of fast electrons, but you get that non-volatility built in.
Right, the memory sticks around. Power off. The magnesium ion is still there.
Which is critical for things like instant-on AI, low-power sensors, edge computing, devices that need to react immediately without draining a battery. Think autonomous vehicles or smart devices out in the field.
Okay, this sounds amazing. But getting chemistry, especially tricky ion movement, to work reliably on a semiconductor production line, that sounds hard.
Or it is extremely hard. There are hurdles on both the fundamental science side and the manufacturing scaling side.
Which is the bigger bottleneck right now.
Probably still the fundamental science.
Yeah.
Because you're dealing with the physical movement of atoms, the signals you get from these devices. They're noisy.
Not as clean as electron flow.
Exactly. There's a randomness, a stochastic nature to it.
Yeah.
Atomic movement isn't perfectly predictable cycle to cycle.
Which makes analyzing the data tricky.
Very. And that's where Schwacke's computational skills come in. It explains why she received the MathWorks Fellowship twice, actually, for her data analysis work using MATLAB.
You need sophisticated tools to pull the real signal out of that atomic noise.
You absolutely do. You need complex models to prove that, yes, this ionic mechanism is working reliably, despite the inherent messiness of atomic movement.
Let's talk about the challenge of just working across these fields. Electrochemistry and semiconductor physics. They're pretty different worlds.
Totally different languages, different literature, different experimental techniques in many ways.
So she had to bridge that gap.
Absolutely. Especially since magnesium hadn't really been used in this specific type of neuromorphic device before, she had to be really creative.
Where did she draw inspiration from?
She couldn't just read papers on semiconductor devices. She had to dig into advanced magnesium battery research.
Ah, back to energy storage tech.
Right, to understand the basic science of how magnesium ions move in solids, the diffusion kinetics, and then translate those electrochemical principles into a computing context.
That ability to connect seemingly unrelated fields, that's often where breakthroughs happen.
It really is. And when she hits those challenges, whether it's the noisy data or, synthesizing the materials just right,
It goes back to the gingerbread.
she uses that same core approach, apparently.
Yeah.
Methodical resilience.
Well, so?
Like with the difficult recipe, right? You don't change everything at once. You adjust one thing,
Yeah.
let the butter, say, and see what happens.
Isolate the variable.
Exactly. She tackles the complex experimental data the same way. Change one parameter in the device or the measurement, observe the effect patiently. That's how you make sense of these really coupled multi-physics systems where everything affects everything else.
So what, for you, the listener, is pretty clear here. This is electrochemistry enabling brain-inspired computing. It's addressing that critical need for low-energy computation as AI becomes, well, embedded everywhere.
This is potentially what unlocks that next generation of AI, efficient enough to run on your phone, in your car, in remote sensors, not just in giant data centers.
And it seems Schwacke understands that doing the science isn't enough. You have to communicate it.
Yes, her outreach work is notable. Still involved with kitchen matters.
Making science accessible. I love the example of using cabbage juice.
Oh yeah, the pH indicator.
To teach kids chemistry at the Cambridge Science Festival. It makes something abstract, like acidity, totally visible and fun.
And it connects back, right? That same core idea of material properties, changing first the cookie, now the cabbage juice color. She's translating that for a broader audience.
She's also involved in building the pipeline, getting more people into STEM, Graduate Materials Council, workshops for robogles at Caltech.
Right, encouraging young women in engineering specifically. It shows a commitment beyond just her own research. It's about the future of the field.
Professor Yildiz had a great quote about her, saying she motivates others to see the beauty and logic in science.
That kind of leadership is crucial when you're tackling such fundamental, difficult problems.
Definitely. It takes a specific mix. Yildiz summed it up well. Schwacke is brilliant, obviously.
Yes, but also persistent and resilient. That combination.
That's what turns the slow, hard progress into something revolutionary down the line.
Couldn't agree more.
Okay, so let's quickly recap the big shift we've talked about. To get to truly green AI, we need to ditch that old hardware division.
Memory and processing separate. That's got to go for efficiency.
And Miranda Schwacke's work shows a path. Using material structure itself. Specifically, moving stable magnesium ions into tungsten oxide.
To let the device process and store information together, right there in the material.
Unlocking potentially massive energy savings that AI desperately needs to keep growing sustainably.
Which brings us to our final provocative thought for you to consider.
Go for it.
Okay, so if the basic structure of a cookie helps us understand material science for chips.
And if copying the brain using magnesium ions could revolutionize AI energy use.
Then what other fundamental structures, maybe in nature, maybe in your kitchen, maybe in everyday objects, are we just overlooking right now?
What simple principles are hidden in plain sight?
Exactly. What basic ideas from totally unrelated fields like cooking or maybe geology or biology might hold the key to the next big leap in computing efficiency? It makes you wonder how often the biggest breakthroughs come not from adding complexity,
but from a deeper grasp of the simple fundamental structure of things.